This is lecture number 9 in the cardio series, and in this one we've got 3 learning objectives here, but really there's not very much new material in this particular lecture, and it's summarizing a lot of stuff that we've covered already. And so if you can remember from previous lectures where we've looked at something like this, this really needs to be your home base. If this slide right here makes no sense at all, then you really should not move forward with this lecture. Because what we're about to talk about is actually a lot of the same events. We're talking about what's going on, where does the aortic valve open and where does it close, mitral valve opening and closing, ventricular filling, ventricular emptying, and things like that. And so this slide right here really needs to make sense, because all we're really going to do is take this slide and just present it a little bit differently, and that difference is going to show up in the Wiggers diagram. So this part here, when you look at this right here is actually giving you pretty much the same information as this. All right, so when I say pretty much, I mean as a theme, it's the same kind of information, but here what we're going to do is that on the x-axis actually is time, and you see here 0.1 seconds, 0.3 seconds, 0.4 seconds. So we're going back and looking at things as they occur over time, and really the only new piece is aortic pressure. So let's break down what we're looking at here. Let me see if I can zoom in just a bit so you can make things out. Oops, I hope that's not too much. When you look here, look at what we have. We have here the, we're going to ignore the ECG portion of this. You have a separate lecture on ECG, and you knew everything you need to know about that. But what I want you to see is, what are these lines that we're looking at right over there? Well, we have left ventricular pressure and then left atrial pressure. And this is... This is pretty straightforward. Again, in a previous lecture, I went through what's happening here with the left ventricle, and I talked about what's happening here at the left atrium and the left ventricle. So this, again, is kind of summarizing things. The other thing we see here, the novel part here, is an aortic pressure. And so what I want to do then is let's just look at what's going on with these different pressures as we go through the cardiac cycle. We see, if I zoom back out here, we're going to see that this purple phase right over here is looking at isovalemic contraction and then ventricular ejection. So what is that? This is going to be looking at really ventricular systole. And then this part right over here in blue is looking at ventricular diastole. So again, systole is this part right over here, and then diastole is going to be right over here. All right, so let's just look at some of these pressures. What I want to think about first is, as we start off that cardiac cycle, let's consider left ventricular pressure and left atrial pressure, and let's just compare those two. What we're going to see is that if we read this out during this phase right over here, the green line represents left atrial pressure, and then the blue line represents left ventricular pressure. Again, these are pressures we're talking about. And so right now during this phase, during this light blue and this salmon colored phase, which line is on top? In other words, which one has higher pressure? And you can clearly see that the green line is on top. So green line is above the blue line, which, again, what do these represent? The green line represents left atrial pressure. The blue line is left ventricular pressure. So it's safe to say that during this window, right where my cursor is, it's safe to say that left atrial pressure is greater than left ventricular pressure. And if that's the case, then okay, great. What is happening during that time? Well, what's happening during that time is ventricular filling. You're filling the ventricle with blood. So is that true? What we have down in this section right over here is volume in the left ventricle. And right now, if we pick it up here, we're seeing that the volume in the left ventricle is right about there, whatever that number is, and let's call it around 120 or so. And then we're going to see that left ventricular volume continues to increase right during this phase, because this, again, is ventricular filling. Now, if you're thinking to yourself, well, that's not really much. That's not really much filling if we're going from 120 to 130. Well, the reason is simply because of the way this artist depicted this slide. So see this salmon color right over here? That salmon color is actually the same as this one. So one more time, this is the same as this one. And so again, we can show you that. If you look here, it says atrial contraction is here, and again, atrial contraction is here. So it's really showing you the same thing. It's just kind of a way for us to see or visualize continuity here. So anyway, left atrial pressure is higher than left ventricular pressure. If we were to take it from all the way back at this point, left atrial pressure here is higher than left ventricular pressure, and this is where we're seeing the bulk of ventricular filling occur, and this is the very tail end where we're going to see atrial contraction. And atrial contraction, we get that final surge of blood moving into the left ventricle, and again, this part, one more time, is the same as this thing right over here, atrial contraction. Well, what happens after atrial contraction? If you remember, after atrial contraction, we're now going to start to see the ventricles start to squeeze. And what we have then is that this part here in purple, as I said, was ventricular systole. But if we break down ventricular systole, we can break it down into these two separate parts where we see isovalemic contraction and ventricular ejection. So again, I'm going to pull back to this slide that we've seen before. Again, what are we looking at here? We're looking at ventricular systole, and systole is going to run from BCD. There's BCD. So this whole phase right over there is all ventricular systole. But this window right over here is isovalemic contraction, which means the ventricle is contracting, but there is no movement of blood. There's no emptying of that chamber. And then at point C, the aortic valve opens, and now we see emptying of the ventricle, again, during this part of ventricular systole. Well, we should be able to recognize that right over here. So what we see is this very narrow sliver where I'm running my cursor. That very narrow sliver is actually isovalemic contraction. So isovalemic contraction happens here, and what that means is the ventricle is contracting, and you see that left ventricular pressure is beginning to increase quite a bit, but we don't see ejection yet. Why don't we see ejection yet? We don't see ejection yet because the aortic valve isn't open yet. But right where that sliver ends, you can see here at point number 6, that's where the aortic valve opens. Now, why does it open there? Because finally, left ventricular pressure is now greater than aortic pressure. If you look here, aortic pressure has been pretty high, and although it gets a little bit lower, it doesn't lower dramatically. So during isovalemic contraction, aortic pressure is still higher than left ventricular pressure. Once left ventricular pressure exceeds aortic pressure, that's where we are right over here. And if you were to zoom in, you would see this is where that blue line initially is underneath the red line. And at this point, right where that aortic valve opens, that's where that blue line jumps, and it's greater than that red line right over here in this section. That blue line stays higher than the red line right over here, which means that left ventricular pressure stays higher than aortic pressure. And again, this right here is ejection. This is ventricular ejection. If I bring that back to the other slide, as I keep doing, this right here is ventricular ejection. I wrote emptying here. Emptying ejection is the same thing. So this phase, C to D, this phase right over here, C to D, is represented by this phase right over here. From this point right where the cursor is, right where isovalemic contraction ends, right to this point where isovalemic relaxation, if we slide down, we'll see that this is isovalemic relaxation, right to where that begins. So this part right over here is C to D on that other slide. Now, what happens? This narrow sliver is isovalemic relaxation, and again, we know what that looks like. It looks like the ventricle is relaxing. There's no change in volume at this point. The aortic valve closes because at this point, aortic pressure now is again higher than left ventricular pressure. Let's see if that's the case. Yep, right over here, the red line, which is aortic pressure, is higher than the blue line, which is left ventricular pressure. So again, this part right there represents isovalemic relaxation, which corresponds to this on the pressure volume curve. All right. Now, once we get to this point, point A, now the mitral valve is open, and now we're going to start to see ventricular filling. And again, remember, this is all diastole. Diastole begins right over here. Remember this, DAB is diastole. So diastole runs all the way through here, but this first section, or this first segment, is isovalemic relaxation, where there's no change in volume. And the second section of this part, which is still diastole, is where the ventricles begin to fill. Where is that represented on the Wiggers diagram? That is represented right over here. Now this is where that bicuspid / mitral valve opens. And when that happens, it opens. Why? It opens because at this point, left atrial pressure is again higher than left ventricular pressure. Now, if we ask the question, well, why does that bicuspid or why does the mitral valve open right there? One more time, why is it opening right over here? Well, it's opening because atrial pressure is now higher than ventricular pressure. Okay, that's fine and good. But why is that pressure gradient such? Is it because A, atrial pressure suddenly increased? Or is it B, because ventricular pressure suddenly dropped? And if you look at this, well, you see atrial pressure really didn't change very much, but we did see a dramatic drop in ventricular pressure. So the reason the mitral valve opens is because the pressure gradient is set up that way. But why is the pressure gradient set up that way, such that atrial pressure is higher than ventricular pressure? Primarily, it's because of this massive drop in ventricular pressure. again, which is this massive drop in ventricular pressure. All right. So what I'm doing here, flip-flopping between these two slides, you really should be doing that on your own. As you're studying this diagram, maybe you put it up on the right side of your screen, and this one you put up on the left side of the screen, just so you can track what's happening in both of these slides. Remember, again, this is left ventricular pressure, left ventricular volume, whereas this is showing you everything that's happening over time throughout a cardiac cycle. All right. So here again, we're seeing ventricular filling. If we step back during ventricular systole, remember, of course, during systole, you're ejecting blood, and so all this volume is lost. And this gap right here represents the stroke volume. Right over here, this segment C to D represents the stroke volume. Again, if we come back here, then what do we see? During isovalemic relaxation, we're not seeing any change in volume in the left ventricle, but then during here, we're now starting to see the ventricle fill with blood. And again, that is right here. We're now starting to see the ventricle fill with blood. Now remember that we get a little bit of a final surge of blood at the end, which leads to a slight increase in left ventricular pressure. And so what ends up happening here, right during the salmon section, that atrial pressure increases. I mean, not a lot, but it's definitely, you can see that increase, and you definitely see a corresponding increase in left ventricular pressure. Again, not a lot, but just a little bit. Well, why is that happening? That's happening because this is that short phase of atrial systole, right? Atrial contractions right over here. And again, on this diagram, that's represented right about there, right at the end of filling of the ventricle, we start to see atrial systole. I know it's not represented on this graph. It's not labeled as such, but why is that pressure briefly increasing just to that point? It's increasing because the atrium is contracting, giving this quick last surge of blood into the ventricle. Now from there, again, keep in mind that this right here where my cursor is, that is the same as this right over here. Okay, again, just kind of okay, anyway, I already talked about that. So this is the same as that. So what do we see from there? The mitral valve closes because the isovalemic contraction begins. So although I've said it before, I'll repeat it now. Why does the mitral valve close? The mitral valve closes because I get a surge in pressure. The mitral valve closes because I see an increase in pressure, and that increase in pressure, again, it's kind of trying to squirt blood back into the atrium, but it fills up the cusps of that mitral valve anyway, and that closes the valve. From there, I'm free to increase pressure as I continue to contract until finally my ventricular pressure exceeds my aortic pressure, which allows opening of the aortic valve. And again, one more time, I know we've done it already. I just want to I want you to see that we're coming full circle. Is that left ventricular pressure is increasing, right? The mitral valve closed here. It continues to increase, and now once left ventricular pressure exceeds aortic pressure, then the aortic valve opens, and now I release my blood. Okay? And so the way this relates, again, to ECG, for my students, not such a big concern. The way this relates to heart sounds for my students, not such a big concern. If you're watching this video and you're interested in those things, please do that. Try to relate what's happening here with the P wave and Qrs complex. Remember that Qrs complex represents depolarization of the ventricle, and you'll see that that depolarization of the ventricle is happening just before ventricular contraction, which makes sense because depolarization needs to precede. The electrical event needs to precede the contractile event. So we're certainly seeing that over here. That T wave is representing repolarization of the ventricle, which can begin as I'm wrapping up that ventricular systole, right? Because there's a whole bunch of ventricle there. And again, that P wave, as you know, represents atrial depolarization, which of course that's going to begin before we see atrial contraction. For the same reasons, same logic as we saw with the Qrs complex and ventricular systole, is because the electrical event, the P wave, needs to precede the contractile event, which is atrial contraction. Okay, and as I said, you can certainly relate those to heart sounds if you wish to do so. All right, that wraps up the Wiggers diagram. There are all sorts of representations of this. They all look the same, but this is just from a different textbook. And if you find this one easier, you may want to pause the video and run with this one. You'll see the same thing is happening here, where ventricular filling, this brief moment of atrial systole here is the same as this brief moment of atrial systole here. Again, just to kind of represent continuity. If you felt like printing this out to draw out yet then another this big surge in left ventricular pressure, if that helps your thinking, by all means do that, or print this out twice and have them overlap so that you can go through 2 cardiac cycles. Okay. Oh, you know what I should mention is that's dicrotic notch. Well, that'll be the last thing here. This dicrotic notch, what are we looking at here? Well, if we just describe it in words, we can say that the dicrotic notch is where, aortic pressure has been declining. We see a sudden surge in aortic pressure. Why is that the case? Because we're seeing a massive filling of blood, and that filling of blood is going to increase aortic pressure. It doesn't increase higher than ventricular pressure because that would not allow for emptying of the ventricles, but you definitely see an increase in aortic pressure here as well. And then what happens is that during this phase right over here, which is isovalemic relaxation, as we see aortic pressure decline, we actually see it suddenly kind of briefly increase before it begins its continuous decline. And we did see that on the other one here. This was the so-called dicrotic wave or dicrotic notch. It's the same thing. So what is it that accounts for that dicrotic notch? So the thing that accounts for that is the elasticity of the aorta itself. Now we haven't, at this point in videos, we haven't gone through kind of the makeup and constitution of blood vessels, but especially these larger vessels, there's a whole bunch of elastic fibers all over the place. So there's a certain amount of elasticity. And so if you can imagine a balloon kind of swelling up with fluid, if you, pumped a bunch of water into a water balloon, then what you can imagine is that as the elastic, the elastic walls of the balloon are stretched out, there's going to be a greater desire to recoil. Again, think of a rubber band. The more you stretch that rubber band out, the greater that pull is to recoil all of a sudden. And that's what actually we're seeing here in that in the aorta. So what we're seeing here is that we have this surge of blood coming into the aorta, and it swells up like a big balloon. And now that we've kind of calmed down on the emptying, meaning that there's no continuity of fluid going in at this point during that isovalemic relaxation, now those elastic walls of the aorta are given some breathing room to now recoil. And as they are recoiling, we're going to get a little bit of that spike in aortic pressure. And that's where that dicrotic wave comes from. Okay? I think that's it. That'll wrap it up for this video. Take some time here to answer some of these questions in the recap. During ventricular filling, who has higher pressure, aorta or ventricle, ventricle or atrium? Same thing during ventricular systole and ventricular diastole. You should be able to answer these things. And what I would really, really encourage you is to stop and make it make sense first. And if you still can't figure it out, then go to the Wiggers diagram and just see which line is on top during those phases. And then that should clarify things to you. Actually, one quick point of clarification. What you might want to do is, so this is ventricular filling. When I say ventricular systole, you might want to split this question up and say, when I say ventricular systole, you might want to say during isovalemic contraction. That's one part of systole, right? And then the other part would be during ventricular ejection. So you might want to actually separate it out that way, since remember that systole itself is going to include both this part here, isovalemic contraction, as well as ventricular emptying. So you might want to break the question down that way. And similarly, right over here, during diastole, you might want to break that down into during isovalemic relaxation. Oops, let's try that again. Isovalemic relaxation, and then again during ventricular filling. And to be honest with you, it's a bit redundant because ventricular filling I already asked you about right over here. In any case, you get the idea. You know what you need to do. All right, that's it.